Welcome back, everyone. And today I'm going to do another challenge. I know you guys like me doing some of these things where I kind of just sit there and analyze an effect that exists and try to replicate it. Dave has, released another one that looks really cool that I'm sure able to reproduce for the most part. It's pretty much a Mobius torus. So it's just kind of like just a circle that twists infinitely. And it's a pretty simple thing to kind of build in theory. Depending on what you use to code it, it can be quite complex. Dave uses processing until it makes things a bit easier. His source code is a lot cleaner and smaller than what I have. But today we're going to build it with raw WebGL and raw JavaScript. Literally have to deal with every little instance of it. And I go a little bit too far, I think, in this video. So it's a bit processing heavy, there's a lot of little nitty gritty things you have to do in 3D to kind of build something like this. So let's get right straight to it. So also then, quickly to analyze what we're looking for. What we're looking for is we know it's a torus, and we've done things like this in the past in previous videos, and so we need to create something in a circular motion. It's not a lathe, but it's just just a tube. So we're creating a tube that connects the beginning to the end, and it's square. So we need a square shape, and we need to connect everything as triangles. So every quad has to be connected in a triangle fashion. And to create a torus, you kind of like at the start of the tube, you start at 0 degrees. And then at the end of the tube, like if you think about it as a circle, you kind of end at 360 degrees. So when the next segment in the line or the next segment in the tube goes from 360 to 0, it becomes like an infinite loop. So that's really all the theory and the ideas behind building something like this. So I guess we can start looking at some of the source code. This time around, I decided to build things in like steps so we can kind of see the thought process behind it. So let's do some basics. So we're gonna have to make a renderable out of it. Instead of most of this probably isn't used because I was doing a lot of prototyping, but basic basic vertex buffer. So instead of using stuff that we have laying around, I'm just going to recreate buffers from scratch again. Why not? If you're new to the series, here we go. We're built, like I said, when we're dealing with WebGL, like we're at a core level, we need the buffers, and we need the VAOs. We got to set up a renderable, all these little bits and pieces. A renderable really isn't nothing except a container for a VAO that has a draw function. That all it does is literally 2 lines of code. It binds the VAO and then kind of just tells WebGL to draw the VAO. Collected a bunch of functions that we've used in the past. I decided to combine them all into a static function. There's a couple of new ones. We used lathe and triangle strip. This one just axis rotation. This one I think uses this uses axis rotation. It kind of creates like a quaternion type of thing. This was a quaternion rotation, so we pass in the array of vertices, a quaternion, and this component length, and it just rotates by that quaternion. Like I said, we've done this a lot in when we're building King Kite's planet from scratch. Through code and without a 3D editor. Simple rotation, translation, centroid, in case you don't know what that is. That's just finding the center point of all your points. So if you have I have 15 vertices, it kind of does like an average and gives me the center point. That's really the whole gist of it. And quad normal. We've done quad normals in when we do raycasting. So this way we can find the direction that a quad is pointing at. So that's why I say it's quad normal. It's the normal direction. I think I optimized this one quite a bit. Yeah, I did a lot of optimization. I put the cross product and normalization all in here. So instead of calling other functions, everything is done in one quick go because we have to do this to a lot of vertices. So for optimization, I took out a lot of function calls and actually just introduced all the mathematics into one function that actually generates the quad normal just by passing in the 4 points of a quad. And from there, it'll calculate the rest. So now that we got the idea that that's a lot of the functionality we're going to use to kind of just manipulate our vertices are right there. So step one, we need to create a shape. So we know it's a square, so we build a square. You got 4 points that defines a quad. Don't need this yet. And we just pass in our vertice array into make renderable and it does the VEO thing. And we get this. And the quad that we're building faces toward the X because we want to make a circular too. So the idea is that we're going to move this away from the center and then we're just going to rotate it. So, like for example, we're going to translate. So we're going to pass in this array and we're going to say we want to move all those vertices 1 unit on the z-axis. So that's the green. So if I click refresh, now it's moved. Another thing we have to keep in mind is that we also want to rotate it. So we can, after that, we can just, again, since we modify the shape, we didn't modify it some more. So we're going to modify by using Y rotation. So now it's at a 45-degree angle. And in case you don't know where 45-degree angle came from, that's rad. That's right here. That's pi divided by 4. All our angles have to be in radians, so we have to use pi as a starting point to get the rotation. And one thing to keep notice is that this animation, these points need to be kind of slanted. They're not perfectly square. They do have to be slanted. So another thing we kind of might have to do is that we need to turn. So let's say if I don't rotate yet. Oh, not my bad. I mean not rotating. Not slanted. Well, it has to be slanted too. But you notice as the quad goes around the circle, it rotates. So, like I said, it starts at 0 degrees, and when we get back around, it'll be 360 degrees. So that's what we're doing here, actually. We're rotating the square. I don't even have to translate it, but on the x-axis. So now you see it's been changed. It's not like the 2 points aren't crossed anymore, like a square. Now it's more of a diamond shape. That's because there's a rotation. So. And another thing we need to keep track of is we need to know the center point. All right, so that's also important. And there's a center point. So we add it to the center, we do an average, and we add it to the end of the shape list. So there's our center point. Now, why is the center point important? The center point is important because we're going to write a shader code that does all the animations. So we're not going to do the animations in JavaScript. The shader is going to do that for us. So in the shader, we're going to have to pass in all the information we need to be able to manipulate the vertices. So if we're going to do rotation and things like that, we need to bring these points back to the origin, do our rotation, and then bring it back to its original position. So that center point allows us to move these 4 points back to origin. So that's what the center point is. It's really just a way to get this back to origin. And the last piece of the puzzle that we need to do this, we need to calculate its normal direction. So even though there's a line here, and it calculates. That's the direction it goes. And the reason why we need the normal direction is that we're going to use quaternions to rotate this. So the idea is we're going to pass in an axis. or we're going to save the axis. We're going to pass, like I said, we're going to pass all these vertices. We're going to pass in the center point for every single one of these vertices that belongs to this quad, and we're going to pass in the axis, its direction vector. So with the center point direction vector, we are able to then move this back and forth in origin, and by using that axis, we can use quaternions to do a rotation on that specific axis. So let's see if I'm going to contort the quad, click refresh. Now you see that the quad now been kind of changed. Now it's rotating, it's kind of angled. Now our direction has changed as well. So like I said, this is the axis in which we use to rotate. So once this is back in the center, we use that as a way to rotate it, to create this effect of a quad rotating. So that's going to be the magic sauce, is that with all this information, the shader can then use a quaternion to, it will actually generate a quaternion in real time to use as a way to rotate the quad for every segment. And each segment is going to have a different center point, and it's going to have a different axis of rotation, which is basically the normal direction that that quad is facing. So yeah. So that's really just step one of like kind of showing all the, so it's like if you're first here building, it's like, okay, what are the pieces you need? You know, like we need the shape, we need to know how to be able to move it, we need to know how to be able to rotate it, what it's center pointed, which is normal. So we're getting all the spices that we need to start putting together our shader, because we need all that information. Now we need to start to formulate a way to build the shape. So in step 2, we kind of build the idea of duplicating our shape and repeating it as many times as we need it. So we have our shape. I'm going to say I'm going to repeat it 3 times. And pi times 2 is 360 degrees divided by steps. So it's 360 degrees divided by 3. So that means we know how many steps we're going to take. Or what are the angles for each step? For every time we do a step, how many angles of rotation do we need to apply? So during while we're creating the steps, we make a copy of this entire array. We manipulate it like we did in step 1, and then we add it to segments. So in the next version, in step 3, segments is going to be different. But right now, it's just a simple array that holds all the vertices. And then we just dump it all into there, and then we pass it into our renderable. Refresh. And there you go. So now we got our shape. Now we know how to rotate it and duplicate each segment. So this way, now we have, like, let's say this is a simple segment. Basically it makes a triangle. But if we wanted to, we can up the ante a little bit. Say 30 segments. Now we kind of have a torus shape built out of quads. Now that the only big step that's left behind is to connect the dots to make triangles. So if I put this back into 3, I'm going to show you this simple basic idea of how to connect the triangles, because that's going to be the next step. The final step is doing all this, connecting the dots, and then applying all the rotations to. So as we're building each segment, do I have it in here? Yeah, let's do this. Let's do that. So for every segment, we're going to rotate. Kind of hard to tell, but if I were to do it again with 30, so this way you can kind of see. Now you see everything's kind of turning and twisting into itself. It's hard to tell when it's so many when it's points. Let me try 8 points maybe. Refresh. Probably hard to follow, but if you can tell, at every segment there's a slight rotation. So we're kind of building this right there. So that's like that. So like I said, we're building each segment. We apply our transformations to it, and we save it out. And that is pretty much step 3. And let me preliminarily tell you how to do the triangles, since the way we have the data. So let me get rid of that transformation of x. We don't need that for this right now. All right, so to connect the dots with triangles, it really depends on the data. So if we're going to connect triangles, or connect the dots to create the triangles so that we can render, the easiest way is sometimes just to group things together as quads, because once you have a quad, it's very easy to break it down into two triangles. And if you have things broken down as quads, then you can apply UV values to it very easily, which allows us to create a shader that colors the lines in the background. Okay, so if you remember correctly, this is our shape. So every shape has a point. So this is point 0, that's 1, that's 2, and that's 3. So in here, that's 0, that's 1, that's 2, that's 3. Now, don't forget, each one is a duplicate of the original. So over here, that's 1, that's 2, that's 3, that's 4. And again, over here, 1, 0, 1, 2, 3. So it starts at 0, 0, 1, 2, 3. So every lower point that's closest to origin is really the 0 index. So now that you see how the points are laid out. Now, like I said, you play a game of connect the dots, and a quick and easy solution, especially when you're dealing with kind of a tube kind of fashion, is that if everything is built off this, if every segment's built off the exact same shape, you can connect the dots very easily in different ways depending on the draw mode. If you want to draw in triangles, you do it one way. If you want to do triangle strips, you do it slightly differently. But overall, it's the same kind of idea. So like I said, we need to group things as quads. So we start with, say, segment 0 and segment 1. So that's 0 and 1. Right? So those are the two segments. So we need to connect these two first. Then we could start with 0 and 1 vertices. So here's 0, here's 1. That's 0 and that's 1. So if we connect those 4 points together, they make a quad. Once you have that quad, you know to kind of just 0 goes to 1 and that 0 goes to that 1, and that kind of splits that quad in half into 2 triangles, and you're done. So you can then create very quickly, very easily, building one quad on the bottom. And the process is a loop. You just rinse and repeat. So you have 0 and 1. So you do those together. Then you move on to the next one, 1 and 2. So 1 connects to 1, 2 connects to 2 over here, and you rinse and repeat. So you say 1 connects to 1 and 2. So it connects to 2. That splits the quad in half, and you're done. And you just save the information that way. Again, like I said, you start with 0, 1, 1, 2, 2, 3, 3, 0. So if you just loop around, you will quickly divide everything as quads in a circular fashion. So you basically just build everything as loops. Since you lay out your data in that kind of fashion, it makes it so much easier. And I build everything as counterclockwise because that's how you have to build your triangles. So I build everything as counterclockwise. So once you go around segment 0 and 1, because again, this is segment 0 and this is segment 1 as opposed to vertices, the process repeats again. Then you go to segment 2 and segment 1 and segment 2, and you connect the dots the same way, every single vertice. Then you go to segment 2 that connects to segment 0, and you connect the dots. And then in the very end, you'll have a triangle, basically, once you connect the dots. And that is how you connect the dots when you're dealing with tubes that have the exact same shape for every segment in the tube. We've done things like this in when we're dealing with Bezier curves. We're removing all our shapes along Bezier curves and then building them. But we use triangle strips. Today we're not building triangle strips because we need actual individual triangles. So the code is was built differently today for this video. So that's step 2, and then we go to the final step. We're done. We're almost done, and we almost got the shape that we want. So we're going to go to step 3. I'm going to set this back to 0. I should have done that beforehand. And I should take this out too. Yes, should take out that for now. So we have our regular shape. Oh, one more thing I need to do. Because since we're dealing with points, now I need to... can I? Yeah, I probably can. Let me see. Let me try this. I'm going to try this shader for now. And then triangles. So because we're building triangles now instead of points. So I think that's enough for now. So this is pretty much the same thing from step 2. Let me do maybe 3 for now. Let's not do 30. So we're going to do 3 points. We're going to try and build that triangle again. And segments is now going to be kind of like kind of an array of arrays. It's going to be an array that holds a segment. So you have segments that has a list of segments, and we're just defining the indices, I believe. Is that the indices? No, these are the actual vertices. These are actual vertices of each segment. We calculate the center point. We calculate its direction. We save all that to the segment so we can use it later. So we need the center and the direction because all that stuff is going to be pushed to the GPU, and then we pass into the segment. Then we have this big glob of code, which is not that scary. It's just long because we're dealing with a lot of points. But we're going to build our triangles, and we're going to build our center, our direction, and our UV. So we have all that information for every vertex. So for every vertex, it gets one of each. So this we're not using element indexes, so just going to be pure, just lots of vertex information because we need individual triangles for this effect, so we can't do indexes. So that's why everything we're going to end up duplicating. So since every quad is going to share the same center and the same direction and the same UV, or the UV is going to be different for every vertex, but it's going to rinse and repeat. Here we have the quad order. I wanted the quad order to be different because we get different kind of looks and feels, I guess. Because I did this is the normal order that we usually do quads, and there was an issue. I can't remember what it was, or it didn't rotate exactly the way it was. But by just by offsetting the order for building the quad, or by splitting the quad apart into triangles, gave a different effect and a different look. I can probably show you how it looks after in a bit. So all this does is it goes through all the segment information. It goes through like segment A and then segment B. And then we connect the dots, like the way I explained it. You know, I just defined the 4 points of the quad. I'm just saving the segment and the index or something. Define the 4 points of the quad, which the segment belongs to, and the index. Knowing its segment means we can pull the relative index. So I'm just doing kind of this annoying way of trying to save all the information of every vertex. Because, like I said, we have to duplicate center and direction for every single vertex. So there's one center value, but I need to duplicate it 4 times for every vertex because that's just how vertex data works. If you need to define triangles individually, you're going to have to repeat a lot of information. It kind of sucks that that's how WebGL and OpenGL works, but that's the, you know, if you've been through me throughout the whole series, you've seen that's why we had. But if you're new to the series, that's why I'm trying to explain it to you. So yeah, so we just have to duplicate for every vertex of a quad. We got to duplicate the center and its direction, and this kind of just makes it easier to do it. That's all. Like I said, so we need the bottom points. So that's what this part is. We're defining the bottom. And over here, we're then defining the other side, this side over here. So this is segment 0 or segment I, 1 and 2, and then segment II, 1 and 2. So that's what I'm doing. That's That's why you see S1 and S2. And I also use I and II for index, whatever. So, and II is calculated by I plus 1 modulus length. So this way, when it reaches the end, let's say, like I said, it's 0, 1, 1, 2, 2, 3, 3, 0. So that modulus allows me to go from, when I hit 3, I go straight to 0 as II. So that's what that is, in case you're new to doing a lot of programming math. So yeah, like I said, I define the quad. Then I use my quad order, or the pattern quad, my quad pattern. And I use that pattern to kind of help build all the vertices. So it goes one vertex at a time. And for every vertex that I'm creating, I'm copying the center, I'm copying the direction. And at the very end, I hard code the UV values for all 6 vertices because, even though you have 4 vertices to create a quad, you require 6 sets of vertices to actually create a quad because you're creating two triangles, and each one has its own set of information. So, yeah, it's a lot of information, and that was really that's it. That's all it takes to build the overall shape. So if I click refresh, hopefully I didn't break anything. Ooh, the browser freeze. I can't rotate. I think I broke something. Shader of null. Oh, because I'm not loading in that shader. Okay, whatever. I didn't load that shader anymore, do I? No, that's why. Okay. Made a mistake. I forgot I wasn't loading that shader anymore. All right, so let's just use the shader I did to render this. Refresh. There you go. And we'll step through this shader in a bit to see how you animate it. But there you go. So as you can see, we have the quad, and it's rotating on its axis. And that's it. And it's just looping through 0 to 360 degrees and back again, basically kind of like in a modulus way, nonstop. And like I said, this is a triangle. We built all the faces. So if you want, let's see. So we can now start tweaking it. So right now, every single quad base every single segment, I should say, because the quads are on the outside. The points that connects all the quads are segments. Every segment has the same rotation. So if we start applying different rotations initially for every quad or for every segment, now we start getting this weird looking effect. Now this doesn't look very, very good as a triangle, but if you up it to, I think, at least a minimum of 8 segments, it starts to look a little bit better. Like starts to look that donut that we kind of want to do. Another thing we need to do. Let me see. Yeah, I want to show that specific problem I said I had before. Let me pay attention to how these lines connect. They're nice and straight. If I go back to use the regular pattern of building quads, the quads will still build, but there's like a weird look. There you go. It's kind of hard to tell, but there's a little break. Like this creates actually a whole completely different shape, which is kind of neat in itself, but it does not generate. There's like that little break kind of when it comes in that this one does not have. It's not smooth. This one makes it more blocky when it animates. So that's why I said by making the pattern customizable, I can actually overall change how it animates. So this one now makes it a lot more smoother animations, just by changing the order of how the quads are laid out. It's essentially the idea that it's dependent. It's where the quad is divided. So instead of going from, left to right, I'm going right to left, I guess. That's why I'm just going the opposite direction. So if you think there's a quad and there's an X, instead of going the / I'm going to the backward slash direction, basically. Now, let's see, what else? So we're getting, like I said, we're getting close to that effect. So we got the rotation. Now another thing we need to do is add a slant to it, because there's quite a bit of a slant. So we just end up just modifying the shape just a little bit to add a little slant into it. You know what, maybe it looks better. Let me up this to 30 now, because let's just go straight for the money shot. So by just upping by 30 segments instead of 8, now we're really, really close to this. But there's kind of like I said, there's like a something distorted. Like I see something in here that's missing in this one. Like everything is too even in this version. So that's why I said if we change the shape, you'll probably notice it better once we have more segments. Refresh. It looks a little bit more distorted when it turns a little bit. I don't know how to describe it. To me, it's not perfect. I love how his centerpiece always stays perfect. Like I said, I might be doing something wrong. Might have something going in the wrong direction or something. But overall, the idea is still there. It is a Mobius strip. So there you go. That's. Oh yeah, and I guess the last part is really the shader. Like this is now that we got the shape working, now we can look at the shader. I forgot the shader. So it's a very simple shader. I copied one of my old shaders. That some things in here that are kind of just not useful. So I saved pi and pi 2 because I think I need pi 2, but I put those in. There's also pi half and pi quarter. I found online, just hard-coded values that we can reuse. And I have two functions here. We have Q rotation, which takes a quaternion and a vector, and all it does is rotates that vector based on that quaternion. Very simple math equation to do it. This one actually generates a quaternion based on an axis and rotation. In radians. So, I'm trying to think. Fract. Okay, so those are the two main functions, and we have pi. So this is our vertex shader. So we're in fragment shader. We're not doing anything special. We're just highlighting anything close to the edges of the quad as black, and anything else is red. So it's very simple vertex shader, fragment shader. Now vertex shader is where all the fun stuff is actually happening. So the real part is, first we're going to make a copy of our position. And remember I said the center point, we need to move it. So all we do is take that center point and say subtract. So we're moving the position back into origin. We're going to generate a quaternion. That's the part I highlighted that's doing. That passes it into our quaternion rotation and our position. So this way it rotates it. And then I move it right back to where it was originally. So that's really the magic of actually doing that kind of rotation. And since we set a default rotation to begin with, everything kind of starting between 0 and 360 degrees, everything just keeps on rotating based off its initial rotation. So everything kind of just flows really well. And by building the axis, I pass in the direction that we calculate. Like I said, in step 1, we figure out what is the direction that the quad that we built, or the shape that we built, is aiming at. And we're using time, and we're using a fract function. And if I remember correctly, fract function creates a sawtooth wave. Images.cool. In case you don't know what that means, sawtooth sawtooth wave. That's the wave it's doing. It creates a sawtooth wave between 0 and 1, right back down to 0, back on 1. So I'm passing time and a fraction of time. So this controls the speed. I can make this go faster or slower, the rotation. So this generates me a value between 0 and 1, but as a linear sawtooth wave. And I multiply it by pi 2. So pi 2 is 360 degrees. So I'm going between 0 and 360 degrees and right back to 0. And that creates a complete rotation. And since everything is built around the idea of 0 to 360, everything can just rotate smoothly together. So, like I said, so instead of using a sine wave, we use the fract function, like a sawtooth wave, which does a really great job. Why not? Let's see what a sine wave does. Doesn't seem to do much. That or probably the shader never. Oh, that's right. Because a sine wave goes back and forth between -1 and 1. So my bad. And it's more of a curve. So it'll rotate one direction, then eventually it'll slow down, and then rotate the other direction. So yeah, by trying different trigonometry functions, I guess you can get different effects. But like I said, a fract creates a sawtooth wave, so it makes it a good function to do kind of just a linear forward motion. If you're, I guess, trying to create that infinite loop type of thing going on. So that's it. So here, like I said, here's the effect. Here's a Mobius torus. I try to get as close as I can, but again, I'm not a mathematician. Dave did a beautiful job of generating it, and here's my cheap version of it. But there's a lot to it. If you don't have a framework to do all this in, even though we do have fungi that we built from the ground up, like I said, in this example, we did a lot. We have to create a shader that does all the work for us. We have to be able to load up and render shaders. We're building buffers, things like that. We have all these raw functions that we kind of had to. I actually had to write not write myself, but like some of these I kind of put together. I think it was the quad normal and the central and the translate. Rotation, I just got some information and built a function based on equations, and these are functions that I think pre-existed somewhere else. Like this function is built off of the shader code. So the shader code that I found like a long time ago how to rotate a quantorian, I went and tried to make a very optimized version of it in JavaScript. So that's what QRotate is. It's the exact same one as the shader one, except shader uses C++ and can overload operators. JavaScript, not so much. So this is the equivalent of this, sadly. I would love to program more in C++. I just don't have time or experience in it enough, but I know enough of it, how it works. And yeah. So yeah, like I said, there's a lot. I did some lathing as a prototyping, but I don't need to lathe anymore. So yeah, I kind of ended up grouping all our procedural generated functions together in one static. So this is a great class to have around if you want. Like I said, it comes with a lot of mathematics. Don't think it has any dependencies, really. No dependencies. Like especially some of the math functions I have, I actually took away all the dependencies for our math library. Like I said, quantorian rotation. Does this one depend on quantorian rotation? No, it's completely independent. All right. Like I said, I went back and just rewrote things and converted things and whatever. So yeah, it's probably a long video. No, not too long, I don't think. There's a lot to, like I said, a lot to explain. I just want to say thanks for Dave for an amazing piece of work. If the internet existed like this when I was 16 and 18, and people like Dave and the web existed to see the beauty of mathematics, I would have gone into this so much sooner in my life. You know, I'm 38 years old, and I've only been doing this for a year and a half. Seriously, I've only been doing this for a year and a half now. It would have been great if I could have gotten into this. Like if high school, like my math teacher showed us the beauty of math, this would have been it. Because I loved art, and I like programming, and I like playing with numbers. But Dave does a great job to really, I guess, inspire people to build art with mathematics. And if you're into graphics programming, that's really the magic. You know, you're turning numbers into these funny, amazing little things. So I just want to say thank you again to Dave for his post. It's really awesome. I did comment, posted my initial screen capture of it. It's kind of, you know, I'm a nerd. I'm geeking out. So that's it. I don't know if I'm going to do any challenges anytime soon. Right now I'm busy with trying to build up some fungi stuff. I want to do armatures again. I need to go back to doing armatures because I really want to start doing games sooner than later. So I've been so busy with other things, especially with shader blocks, my new open source project that a lot of people are kind of interested in. I just don't have time to dedicate to that because I need to dedicate time between 3 or 4 different types of projects, and then I spend time doing these challenges, which takes away time. But like I said, I do these for fun. I do these to challenge myself to see how well I'm getting at seeing an effect and trying to reproduce it with the knowledge I've gained doing WebGL for the last, I guess, year and a half. So hopefully you guys learned something new, something interesting. I guess I'll see you guys at the next video, and please like and subscribe, and see ya.